Thanks for taking the time to come back and see part 2 of our Amazon DynamoDB Advanced Design Pattern Sessions. My name is Rick Houlihan. I am a Senior Practice Manager for the DynamoDB Service Team. As many of you know, I've been involved heavily over the years in building and helping the DynamoDB community be successful. With this year's session, again, online, gives us a little flexibility. We can start to look at doing maybe some live demos that would be logistically difficult in a live session. So let's go ahead and talk about what we're going to be diving into in this part 2. Again, if you haven't seen part 1, please go back and take a look. We got some good content there as well. All right, so this session we're talking about pessimistic locking. I have concurrent processes accessing items on multiple partitions, and I need to make sure that the data in those partitions is consistent as writers come in and update across multiple items. Shard key optimization, what does that mean? Sometimes users have relatively small tables. I don't necessarily have millions of WCU to allocate to generate a table with 1,000 partitions. So I'm going to need to generate optimized shard keys to guarantee that if I have a table with 10 storage partitions, that I can actually deliver 10,000 WCUs in an aggregation workload. How are we going to make that happen? I'll actually show you how to do that in code, and we're going to see it happen in real time. The last thing I'll leave you with, a lot of people talk about, and there's a lot of debate over the single table versus multi-table design. We're going to break this down. I'm going to show you the actual data deployed across multiple tables. We're going to talk about visualization of that data. We're going to look at actually what does it take to execute a workload across multiple tables versus a single table for a very simple access pattern, and how that the performance of one versus the other. And you can make your own decisions, when all is said and done. All right, so let's get into the first topic of the day. This is pessimistic locking. We want to talk about let's say a workload that I recently worked with a customer on where Transact Write API didn't cut it for them. They had a data analyst, 500 data scientists working on engaged in market research. They were aggregating anonymized customer portfolio data from multiple brokers, and they would see random low frequency imports from multiple sources throughout the day. They had a strong consistency requirement, obviously. So what happened when a portfolio updated, it just kind of replaced the existing portfolio, and they just kind of blew away the partition space for that portfolio and reloaded it with multiple items. So they need to make sure that readers were not reading the data while this was happening. Again, it wasn't happening at high velocity, but it could happen randomly, from different sources across multiple portfolios, throughout the day, throughout the week, and whatnot. So the way we did this was we created semaphore items on the table. Right, every policy, every portfolio, partition on the table had a semaphore item loaded into it that contains some lock attributes. And to obtain a write lock, process would come in, it would update the item and would say, well, set this write lock to true as long as the write lock is false. And while you're at it, set my write timeout to X. Then it's going to return all values from that update and look at the reader's counter. If the reader's counter is 0, it moves on, does its update and whatnot. If not, then it's going to pull back until that reader's counter drops down to 0, or the read timeout expires. If one of those happens, then he's free to go, and the writer goes ahead and updates the portfolio partition, right? So it's a pretty quick process. It's not like it takes, hours to read a portfolio. Those timeouts are short-lived. We just want to make sure that no data analyst is coming into the system and saying, get me data for portfolio X, while the broker is updating that particular portfolio's data set. That's all we're trying to do. The read lock is another side of this equation. A reader comes in, and before they actually read the portfolio, he needs to obtain that read lock. What that really means is I'm going to set the reader's counter. I'm going to increment it by 1 because I'm a reader. I'm not going to prevent other readers. I'm just going to increment that reader by 1, and I'm going to set the read timeout to what what's going to be my read timeout. Now the next reader is going to come in and reset that timeout, but that's fine because it'll be a timeout that's later than mine. So as long as I know that the writer's not going to go until my timeout's expired, I don't care what happens to the other reader, right? And then that just goes on. So the reader is going to poll, as long as the write lock is true, the reader will pull back until the write lock becomes false. And if the write timeout expires, then the reader calls an error handler. So it's the read side that calls the error handler. The write lock is free to ignore the read timeout. He doesn't care. You could call an error handler there to clean up whatever stale reader process there is, but you really don't need to, because when you're done writing the portfolio, you're just going to reset the entire semaphore item to an initialized state, right? 0 readers, null timeouts, no lock, and then you just move on from there. Okay, so that's what this process, from a process perspective, that's kind of what this looks like. The reader sets that value. He's going to block any writer from accessing the table until that read timeout goes down to 0. Once the writer sees the read timeout go to 0, he's going to start updating the table space. When he's done, he's going to come back and update that write lock, which is going to free the readers to continue to read the partition. So we're just using an item on the table that's associated to the portfolio partition as a semaphore to block writers when readers are accessing the partition and allow readers to know when the partition is clear to be able to be read. And this works in a partition, it works at the item level, it works at the table level, it works across tables, right? You can have a lock table that locks multiple other tables for readers. It all works, right? We're going to actually take a look at the code now and dive into that and actually execute this workload on EC2 instance up there in US West 2. Let's take a look. Take a look at the code that we're going to be running for our demo here. We've got two classes that we're interested in, the reader and the writer. The reader is going to come in. He's going to take any random portfolio from the list. We're going to be running this test with 5 portfolios, 10 shards each, 500 items per shard, so about 5,000 items. So he'll be able to load these things pretty quickly. We're going to be running 5 readers in parallel and a relatively small data set because we're trying to execute this test. It's showing us these lock collisions, right? So we need him to be reading a lot of portfolios quickly. As we come in, we're going to, as we establish the read lock, that process is simply incrementing the read counter. And what we're going to do is add 1 to the existing read counter on the item. We're going to set the read timeout to the timeout for this process, which is about 2 seconds. We're going to give ourselves to execute this read. Every reader is giving itself 2 seconds, so the last one to update is going to be the only one I worry about. The guys that were done before, if they're not done by the time the last guy's done, then they're all expired anyways. We've got a condition expression here that says write lock equals false. We're not going to increment the reader unless the write lock is false. If the writers come in and set that lock to true, then we're going to detect the write lock, and that's what we're going to log here in the condition check failed exception. And we're going to retry 5 times. If we haven't got done by then, that's a deadlock. We got to implement an error handler. I haven't done that. Lots of ways to do this. It's up to you, but in this particular case, we just said 5 retries and go. My tests haven't ever produced a deadlock, but that is where you would insert that error handler code. All right, let's look at the writer. The writer does pretty similar operations in reverse. We basically pick a random portfolio and load it instead of read it. We're going to go ahead and lock the item, and the only real differences here from the code perspective are the conditions that we're executing on. We want to make sure the write lock is false. Also, because if another writer is writing, I don't want to overwrite his lock. I'm setting the write lock to true, and I'm returning all the new values, right? All the updated values, because I want to check to see if there's any readers, and I don't want to have to go get the item. Since I've already touched it, I might as well just go return it, and then I can check to see if the readers are greater than 0, or if the read timeout has expired, and if either one of those conditions or both those conditions are true, right? Readers are greater than 0, lock timeout is not expired, then we're going to go ahead and wait on that readers for 200 milliseconds, update the item again with the new timeout for the write operation, and return those values and check them again, right? Pretty straightforward process. Once we get through that chunk of code, that's that blocking code that keeps the writer from updating the items while the readers are actively reading, then we're going to go ahead and just load the portfolio and release the lock. When we release the lock, we're going to set the write lock to false and with the readers to 0, and move on, right? So again, we got 1 writer thread, so we don't have to worry too much about concurrent writers. We've got many readers. We want to make sure the readers aren't reading while the writer is writing, and that's what this code does. So let's see what this code looks like in execution. We've got 2 instances up there in US West 2. I've got a reader on the right. I've got a writer on the left. Let's go ahead and start the readers up, and you can see what's happening. We're just clear the data off the table that exists. We write some new items, and we start reading. Again, 5 threads reading randomly. Let's go ahead and start the writer up, and we can see how those locks start hitting as we start to see those skips in that output stream on the reader side. Those are actually locks that are coming in, and let's go ahead and pause on this. We can actually see write lock detected on P0, a couple other threads firing reads on partition 1, eventually lock releases, and we can go ahead and read P0 again, and that's we can actually see how fast this is happening. Each one of these reads in about 15 milliseconds, 15, 20 milliseconds. So again, really fast process. We don't necessarily have to worry too much. I can go ahead and fire that process back up again, and we can start seeing those locks hitting the table. It's really easy to manage this. This is a great technique to be able to manage concurrent access to those items on the table. All right, that was a great way to be able to lock those partitions and prevent those concurrent processes from colliding with each other. All right, let's take a look at optimizing shard keys. What does that really mean? Well, when you talk about NoSQL databases, it's really about getting that data spread out, right? And DynamoDB is no different. They're all the same. To get the most out of DynamoDB throughput, really any NoSQL database, we want to create tables where the partition key element has a large number of distinct values, and values are requested fairly uniformly as randomly as possible. And usually this means for high velocity workloads, this means typically some process, some implementation of the process we call right sharding. A lot of people are familiar with that. We want that access evenly spread across a key space. We want those requests to arrive evenly spaced in time. The first is easy. Again, we can design the database and the data model to be able to accommodate high velocity aggregations by sharding. Time a little bit less, a little harder to accommodate, but there are patterns for that. Again, but if we get it done right, this is what that looks like. This is a very high velocity table. This table space is operating in the excess of 400,000 WCUs, and you can see from this heat map how much activity there is up and down across that key space. That's really what we want to see. You want to see a relatively high level of utilization across the key space. We don't want to see vertical or horizontal lines, big red lines, right? We want to see these types of even distributions. In order to do that, when we need to aggregate at high velocity, we talked a little bit about that workflow of needing to, aggregate customers by source, products by, product ID and state. We get into this situation where we need to spread that data out artificially sometimes, right? In the case of the table, the customer aggregation is not all that hot. Customers don't order items all that frequently. But in the case of the indexes, in order to support the high velocity aggregations on the GSI, we need to kind of salt those keys, right? If I'm indexing the source, if I'm indexing the product ID or the ASIN, we know these things are going to be getting inserted onto the table at very high velocity. If I'm trying to group those things or bucket those things into those partitions on the GSI, I'm just going to create hotkeys on that GSI and create that GSI back pressure, right? So we want to write the data out across many partitions, but sometimes not so easy to make that happen. What we need to do is make sure that the table space has an even number of partitions and the keys are distributed evenly across that key space. So in order to do this, one of the ways to accomplish this is to use a sample table within your account space and just insert some donor items and then parallel scan. And why? Because parallel scans execute in segments across the key space. As you can see from this chart, if I execute n threads in a parallel scan or n segments in a parallel scan, I'm chopping that table into n number of segments. And if I pick one of the keys that are returning in one of those segments, well, then from all of those segments, pick one. I'm going to end up being very evenly distributed across that key space. So if you have a small number of partitions on the table, this can really help you. And let's go ahead and demonstrate, what that actually looks like when we run some actual code up on EC2. Okay, let's go up to the console and look at the table that we're going to use for this workload. We've got a single GSI configured on this table. We initially deployed at 100,000 WCUs, 100,000 or 10,000 RCUs, and that's going to give us 104 partitions. That's one for each 1,000 WCU, one for each 3,000 RCU. And we're going to insert items at a high velocity onto the table using a UUID as a partition key. So that should cause those items to get randomly distributed nice and evenly across the table space. But we're going to be funneling all those items into a smaller number of partitions on the GSI using a right sharding algorithm. And let's take a look at the EC2 instance that's going to run that workload. We've got some Java code deployed up here. I'm going to insert 100,000 items as fast as possible. Again, because of the number of partitions we have on the table, that insert should occur very quickly. But we're only going to use 100 partitions on the GSI. So every one of these items is going to have the same GSI PK with a random 0 to 99 suffix that's going to differentiate them. So again, they're going to be relatively evenly distributed across those 100 logical keys. But when DynamoDB hashes those partition keys and inserts them into a storage node, it's unlikely that it's going to be well aligned. If I only have 104 storage nodes, I'm not going to be able to right shard across 100 partitions using a generic algorithm like this and have them evenly distributed. We're going to see certain logical keys doubled up, tripled up, and if you just do the math, I'm doing 100,000 items, 100 partitions, that's 1,000 items per partition. Well, I can only deliver 1,000 WCUs per storage node, so if I'm doubled up, tripled up with these logical keys, I'm asking some of those nodes to do a lot more work than they're capable of. And that's going to cause that index lag that we're going to go ahead and measure right now. So let's run this workload, clear the items from our last run, and then quickly insert 100,000 new items onto the table, and then scan that GSI to start looking at that replication lag. You can see what's happening here, 3.8 seconds it takes to clear the data. And in the initial pass, we got 90,000 items, about 90,000 items, and then it starts slowing down. And this is because those nodes that are doubled up and tripled up, well, they're actually having to wait a second for their token buckets to refill so they can accept more writes. So even though the vast majority of items replicated very quickly, there's a certain number of storage nodes that have a backlog or some sort of back pressure, not enough to cause write throttling on the table. That's typically not going to occur until we see about 30 seconds worth of backlog, but enough to slow things down. And we're seeing that with this, a nearly 4-second replication lag. So there's two ways to fix this problem. The first way is to increase the number of physical or logical keys that we're sharding across, which is then going to cause that workload to distribute more evenly across those physical storage nodes. So let's go 10x. Let's say we're going to use 1,000 partitions on the GSI. Again, we're inserting 100,000 items, into the table. So this kind of means that we're going to have 100 items per partition distributed across 1,000, logical key values, and that's going to much more evenly distribute things. But as we can see, when we actually run the workload, it doesn't really get rid of it, right? And it does a pretty good job, but it makes the read pattern much more complicated, right? If we look at this now, I'm down to 1.8 seconds replication lag versus 3.8. But so less than 50%, but I've got a much more complicated read pattern. I've sharded out across a much wider key space. And so a better way to do this is actually to go ahead and generate optimized keys. And so let's take a look at some of the code we can use to do that. It's not complicated. Instead of just creating random 0 to 99, what I'm going to do is pre-generate a well-distributed collection of partition keys, of logical keys. And the way we're going to do this is determine how many partitions we want to calculate for. We're going to load 10,000 items across the key space, using that schema that we talked about for the partition key, key value hash 0 to n. In this case, it's 10,000, and we're inserting one item into each one of those logical partitions. After we finish that insert, we're going to do a parallel scan on that table using the number of segments that we're expecting to generate keys for partitions, right? So if I have 100 partitions I need to spread across, I want 100 well-distributed keys, I'll execute a 100 segment parallel scan, and that brings back 100 100 lists of items. And so what I'll do then is go through all those lists, take the middle value from each one of them, and add that to a list of well-distributed keys. And instead of now using random 0 to 99 as the suffix, I will select a random value from this list of 100 keys and use that value as the suffix. And now I'm actually guaranteed that my logical keys are all going to be well-distributed across that key space. If I have 104 storage partitions on the key space, and I use this pattern, I should end up with more or less 100 logical keys nailed to each one to its own storage partition. So let's see what happens when we actually execute that code on the table here and what impact that has. We're going to take it back to 100 partitions. We're going to add the optimized flag, and that's going to tell this Java application to go ahead and use that little set keys method that we just looked at, and you can see what ends up happening here. 1 millisecond. Okay, that's an amazing difference between using 1,000 partitions and a straightforward random 0 to 99 algorithm. When I use those optimized keys, the performance impact is tremendous. All right, pretty impressive display there. And again, I think I don't know if I mentioned it in the demo, but it really only took a couple hundred milliseconds to find those optimized keys. Definitely something that to keep in mind if you're working with smaller tables. You need even spread to be able to maximize throughput, even spread of those logical keys. All right, so final thing we're going to go through. This is the single versus multi-table shootout. As many of you know, I'm a real strong advocate of getting as many types of items on the table as you possibly can fit. Do whatever makes sense, though, obviously, for your application. If you have, there's always reasons to use multiple tables, but one of them is not because I like to look at my data in pretty normalized models. tables, right? All data is relational. We know this. Everything application you're building has data that's relational, and the applications that we build are used to working with that data in bits and pieces, right? Not big, giant, large, hierarchical chunks of data. They want rows off of tables, not big blobs of data that represent all the rows off of all tables. And the way we do this in a relational database is, again, we distribute those rows across tables. We use those SQL queries to query across those tables in a simplified product catalog like this. You can see all those common relationships, right? One-to-one between products, books, albums, and videos. Product albums and videos, albums and tracks, one-to-many, many-to-many between videos and actors. And again, you can imagine the queries we'd have to run to be able to execute to get just a list of products, right? So potentially a simpler approach might be, and in this case might work, these blobs, these product blobs, where we actually collapse those hierarchies into single items. Generally speaking, that's not the best approach, but sometimes it is. In this case, we really just need these product blobs. So let's go ahead and denormalize that data into this product information that gives us the ability to select all products from our catalog. Now, if we had other access patterns, right, we might want to actually split this data up, and we'll show you how that works when we actually look at the cost and the form factor of a single table versus multi-table. So let's take a look at that cost. If we get into what those ad hoc joins are actually doing to the system, they're causing us to iterate collections. They're iterating even indexes. I'm going to have to scan multiple indexes to be able to join two tables. I have to scan even more to join three, and it even gets more and more complex. And I don't know any of you guys who've worked on relational systems, but the SQL you're looking at on the left here, that's pretty lightweight SQL, right? I mean, the stuff that I've seen in production systems is incredibly complex compared to this. So you can imagine what those systems are doing underneath the covers. That's all CPU cost. And really, what are we doing? We're generating result sets that are kind of common, result sets that are representative of a finished a query, and we're doing it over and over and over again, millions and millions of times a day, and we're causing the system to generate a lot of CPU churn to make these things happen. So, maybe a better approach is to take all those rows from all those relational tables. And again, this might be a little simplistic as well, but we're going to take all those rows and we're going to stick them right into this table and show you how organizing things in partitions gives us a lot of flexibility, basically almost as much flexibility as you get from that relational database, especially depending on how you structure the data and some creative denormalization, right? So if we look at what we've got now are product partitions. Partitions contain many items. In the case of a book, we have the two tables that were combined into a single item. It's a one-to-one join. We could separate those into two items if we wanted. For this purpose, I just stuffed them together in the same item. And I select by book title, I get all of that information. I get that pre-joined data, so to speak. This is really what these partitions represent. Select by album title, I'm going to get the album item and all of the tracks that come from the tracks table. They're all together in a single partition with a single simple select. And the time complexity here, right? No matter how many tables I add to the join, really, how many types of items I add to the join, the time complexity stays constant. If we look at the movie title, select where movie title equals X, I'm going to get the item that describes the movie. I'm going to get an item that describes each actor's role in that movie. And if you look at this construct, it's really more like a directed graph, right? The movie is one node, the actors are other nodes, and the movie's aware of their relationship to the actors, but the actors are not. That's a directed graph. There's ways to make this undirected. We'll show you in a second. As a matter of fact, right now, when we flip that sort key and the partition key, interesting things happen. Now we enable a whole new set of access patterns. Select where the author equals X. I get all the books written by the author. Select where a song title equals such and such. I get all the albums that song has appeared on, all the tracks that were recorded for that song across all the albums it's been on. Select by actor name. Hey, I get all the actors' roles that he's played across all his movies. And so this is kind of that IMDb workflow here, right? On the movie side, I look at the movie, I get a movie summary, I get some top level information about the actors. I don't necessarily get all their information, right? I'm not going to project the actor's bio, for example, into all those edges because the bio changes a lot. And that would cause me to have to go churn the data. But, the actor's role doesn't change. He played that role in the movie. The actor's gender is unlikely to change. The actor's birth date is certainly not going to change. So, these are things that are very safe to denormalize. And I got a lot of people talk to me about, but when you denormalize the data, isn't that being destructive? It's harmful. It's going to create data corruption. Well, if you denormalize data that's immutable, No, it's not harmful. I don't know what to say. If you never change the data, you never update the data, then all I'm doing is using a little extra storage space, right? And so I get the data purists that don't like to see multiple copies of data. Honestly, even if the data changes, if it's not changing at super high frequency, Streams and Lambda is a fantastic mechanism to maintain those updates, right? So things like, employee salary or employee's role and position, these aren't things that change 100 times a day, 1,000 times a day, right? They'll change once or twice every couple of years. So, let's go ahead and denormalize the data and worry about updating it when we need to, because it's really not all that painful, especially when we have things like Streams and Lambda today. It's not 1980, folks. All right, let's go take a look at the other access patterns. Select by director's name. We can get all the movies by given director. Select by musician. We get all the albums a given musician is produced, right? I mean, it's a very flexible pattern, and for people who've never used it, it can be unfamiliar, it can be scary, but when you really start getting into it, it's pretty easy to use. All right, so the other reason we want to talk about single table versus multi-table is performance. So let's get into what that actually looks like in this demo. Okay, let's take our last trip up to the AWS console, see what kind of infrastructure we have now. I've got many tables deployed here, customers, invoices, order items, orders. I got a full online shop. The single table representation is the data table. It has all of those items stored on a single table. All those individual named entity name tables, they contain individual item types. Usually people start to ask questions like, well, geez, when I look at this single table, it's got all these different types of items on it. That confuses my brain. How do I visualize the data? And I ask the same question I always do, which is, so how do you do it with MySQL Workbench? How do you do it with, your on your MS SQL server, right? You execute a query. What happens when I execute a query? Well, some subset of that data comes back, and it's data that makes sense. It's all grouped by order ID. If this was a MySQL Workbench or something like that, we would just simply see a join, view. And in this case, we see all the individual items. It's the same result set. We have the order, the invoice, the order items, any shipments that were made, shipment items, the whole 9 yards. So it's actually quite easy to visualize the data when it lives on one table, because NoSQL databases don't have join operators, right? So if I want to go get all this data, imagine what I have to do here. I can go to the orders table and I can query for 0653 and I can get that order, and then I can open up another window and query another table, open up another window and query another table, right? Visualization gets actually a lot harder when you start pushing it across multiple tables. So the next thing I want to talk about is performance, right? Performance is something that is just undeniable, and when we look at the actual code we're going to run here, it gets pretty obvious why it's faster to run a single table, right? I've got a single runnable task executing on this thread pool on my single table configuration. If I'm coming in with multi-table, pass, and that's what we're going to do. The first pass through is going to run multi-table. The second pass through is going to run single table, and then we're going to report the efficiency of single table as a percentage of the time it took to complete compared to multi-table. And you can see just very clearly we have multiple, one task executing here for a single table versus 5 tasks executing. And again, these are all in parallel. This runnable, these are runnable tasks that are executing. Each one of these things initializes itself, sets its own query spec, returns an item collection to an array list, and posts it onto the results. As we exit the thread or enter the thread, we're incrementing the thread count. As we exit the thread, we're decrementing the thread count, and that's what we're waiting for here. While the number of threads executing is greater than 0, we're sleeping for a couple of milliseconds and trying again. So there's just no way this code is going to execute as fast as this code, right? 5 tasks just don't execute faster than 1 task. And it takes a lot more resources, right? So let's take a look at the EC2 instance that we're going to use to actually run this code. I've got this code deployed up in US West 2. It's going to hit that table collection that we just were looking at, and it's going to, and again, report the results based on the amount of time it takes to do multi-table versus single table. So it's obviously executing faster than we can see right now, but let's go ahead and stop that test. You can see what's happening here. Single table is 20% compared to multi-table, 30 milliseconds versus 143, 35 versus 148. It's just never going to get better. It's always going to stay the same. You could run this test for hours and hours and hours, and you may find 1 or 2 requests in that whole bunch where that single table query ends up actually being slower than all 5 of the multi-table queries, but it's just unlikely that you're going to get the same type of performance back, even though we're retrieving the same number of items. Right now, don't get me wrong, this is not 1 request. This is 484 requests. It's actually a lot more than that. It's 484 times 5. In this case, it's 2,400 2,420 requests. In the single table query, it's 484 requests. So you can see how it just blows up at scale, right? So again, single table is going to always be a lot more efficient. You're going to use less resources. It's going to require less infrastructure. It's going to process your data more efficiently. It's just going to cost you a lot less money. In case you missed it, let's go back to part 1, take a look at that, and get into the fundamentals of NoSQL as well as our first couple of design pattern examples, including operational analytics, summary reporting, and aggregations. Pretty cool stuff. Related sessions. You definitely want to hit these sessions. This is Alex Debris, author of the DynamoDB book. I love what Alex is doing and other members of the serverless community and DynamoDB NoSQL community, being able to bring this serverless or single table design patterns to everybody. And Alex has put together a really tremendous resource there. Definitely recommend you go out there and check out that book, check out these sessions, and thank you very much for taking your time out of your day to come hear me talk.